Uh, Good evening, everyone. So we'll start the lecture just in a bit. Till now, we have discussed about the application layer protocols and discussed what are the layers which are present on the uh, this computer networks, like how the network protocol works. What is the major network protocol? So that is the network protocol that we are following is the TCP/IP protocol, and for that TCP/IP protocol, we are now following understanding each of the layers individually and understanding what are the protocols which are present at the individual layer. So from the previous lectures, we have studied till now about the application layer protocols like STFT, then HTTP, then SMTP, then the language which is used, that is HTML, and so on. So if we firstly in this lecture, we will first start about discussing uh, the assignment which was given to you the last week, and that is assignment number 2. Let me first admit all the attendees, and then we can start. I assume that everyone has done assignment 2 and you all have seen the solutions as well till now. So we'll discuss the solutions of assignment number 2 that was given to you last week. I would like everyone to put up your answers on this screen if you know the answers. So first question is, what is the command used by DNS to translate a fully qualified domain name into its corresponding IP address? So we have studied the domain name space, and we know how to convert how the domain namespace help to translate a fully qualified domain name into its corresponding IP address. These are particular commands. So can any one of you tell which is the command which is required for it? I would like to have answers. Okay, so guys, let us make this session interactive, and I would like if everybody would answer and discuss, have a good discussion. Yeah, so it is NS lookup. Answer is C. So it gives a fully qualified domain name. NS lookup provides its corresponding IP address. Okay, on the top of which protocol TFTP is built? Internet protocol, file transfer protocol, or hypertext protocol, or none of these? Anyone? Okay, so the answer is D. TFTP is implemented on the top of user datagram protocol. As we discussed, FTP, which is a reliable protocol and it is built on the top of TCP. But at the same point, TFTP is built on UDP. So which of the following is the correct syntax for anchor tags in HTML? We have studied anchor tags, if you remember. These are used as for the user link or the hypertext link. So any one of you can tell what is the correct tag for anchor? Yeah, so correct tag is B. So anchor tag is it started with A and ends with A, and it includes the link or the URL link from on which you want to access. And at later also you can also provide the here this keyword which serves as the keyword on which you will press and you will be redirected to that particular link. The next question is which of the following port is used for secure file transfer protocol SFTP by default? So we have discussed few ports which are corresponding to the multiple different protocols. So any one of you can tell what is the default port number for SFTP secure file transfer protocol? I want responses, so it would be good everyone if you can interact. So correct answer is 22. SFTP uses port 22 by default. Okay. Now next question is that consider the following two statements and choose the correct option. First one is that Google Chrome or Internet Explorer can be used as an HTTP server. And second, Apache Tomcat is an HTTP client. Only one is correct, only second one is correct, both are correct, or none of them are correct. So you have studied HTTP protocol. In HTTP protocol, the web browser acts as the client and web server act as the server. So here, none of them are correct because the Google Chrome, which is or Internet Explorer, which is the web browser, is said to act as HTTP server. However, it is an HTTP client. So Google Chrome and Internet Explorer are HTTP clients from where requests can be sent, and Apache Tomcat is an application container that serves as an HTTP server. Next question is consider different activities which are related to email. So M1 is the operation. There are multiple operations defined. So M1 is the operation which sends an email from a mail client to the mail server. M2 where it is download an email from the mailbox server to the mail client. And M3 is checking email in a web browser. So what are the application level protocols which are used in each of these activities for M1, M2 and M3 correspondingly? There are four options provided. You can see them and just let me know what are the possible different protocols which can be placed here. So sending an email to the mail client to the mail server, that part needs to be done by SMTP. We studied it, sending mail transfer protocol, the secure mail transfer protocol. Then downloading an email from the mailbox is done by POP protocol. And then checking browser is done by the HTTP protocol. So which of the following HTTP methods request information about a document, but not the document itself? Get, head, put, or post, which requires information about a document, but not the document itself. Okay, they're all saying head. So the answer is right. The head method requests metadata about a document, but not the document itself. Next is consider the following statements and choose the correct option. One is SNMP v3 ensures the message cannot be read by an unauthorized entity. Next is SNMP v3 cannot ensure the validity of source from where the message is sent. So there are the four options. You can select which one is correct. Wait, I think many of you have not have the access to chat. So here the answer is B. Only second one is correct. So its explanation is that SNMP v3 ensures that the packet has no longer been tampered with integrity. And second, the message is from the valid source, that is validity, and a message cannot be read by an unauthorized entity, that is the privacy. I don't know why you guys have no longer the access to chat. Anyone? You don't have a Teams account? It's not C, because second, this first one is not correct. Ensures that the message cannot be read by an unauthorized entity. Uh, okay, yeah, that is correct. Like both should be correct. Yes, the answer provided I think is wrong. So both should be correct. The message cannot be read by an unauthorized entity and cannot ensure the validity. Um, uh, No, so the answer should be A, that only one is correct, because this second one is not correct. It is ensuring that it is from the valid source. SNMP-v3 does that. But here the second statement is wrong. So the answer should be A. That it cannot ensure the validity from the source. However, this ensures that the message is from the valid source. So only A is correct. Uh, Okay, so you can mail the major the professors and the other team the TAs which are there for the particular assignment, and you can ask them to change the option and recheck their assignments, because I'm the NPTEL TA. I have no authorities in that case to recheck or recorrect your assignments. So you can ask the normal TAs of the course affiliated to. The name of the TAs and the information is mentioned on the course webpage. Okay, I'll ask, sir. I mean, I know who the TAs are, so I'll ask them to react to it once. No issue. So, next question: which of the following HTTP status code is returned when the request document is not found? So, we have studied last time which are the codes which are returned when the requested documents are not found. Yes, it is 404. So which of the following is or are not an application layer protocol? This is the very simple, I think everybody knows. Yes, right. It is UDP, which is a transport layer protocol. Okay, so we are done with this assignment. So now let us first discuss today's lecture, like what the brief summary of what is being taught in this week, and then we will move forward for the next assignment, the type of assignment which you'll be getting in the upcoming week. Okay, so this is the session, third session of NPTEL, and it talks about majorly the transport layer. So as you can see here, this is the protocol that which we are obeying, that is the TCP/IP protocol. And there are these layers, that is, it starts from the application, then transport, then network, then data link layer, and the physical layer. So all of these layers are necessary for the end-to-end device connectivity. However, if you see here, these are the routers. These are the routers. These are the hubs devices which are having only the physical layer and the data link layer, because these are the L2 layer 2 switches only. So till here, these devices only layer 2 protocols are present. Then we have the routers which is called the L3 switch, and here we have the physical layer, then the data link layer, and the network layer. So this is called the L3 switch. But the transport layer is only present at the end device. It is not present between the devices in between, and it follows to maintain a connection between an end-to-end device. So basically, you know that the physical layer majorly works on the hardware level. The data link layer works on the firmware and device driver level. But then the network transport and the transport layer, works on the software level or the kernel level, that is the in the OS of the system. The transport and the network layer follows the OS of the system, that is the kernel level. So how the application data passes through different layers. We have studied that the application layer is the layer which follow obeys different protocols for communicating, or the end to end, that is the applications for end devices. So these are kind of the applications at the end devices, and how these applications interact with the OS. These are the protocols which are followed by the application layer. The application layer has, for example, if you are following the HTTP protocol, so has the HTTP data and a header associated with it. Then it moves to the transport layer for the communication between the systems and adds up a TCP header. Then it moves to the network layer and adds up an IP header to which IP address it needs to be transferred. Then moves to the complete thing, adds up to the data link data layer data, and adds up a MAC header at the data link here. And finally, at the physical layer, the complete set adds up a physical header and a physical trailer to mark the starting and the end of the data which is being transferred from the application from one end device to the another end device. So now we see that what are the typical services which are offered by the transport layer. So in case of the network, the network layer helps to transfer the data from one node to another, but that data transfer or datagram delivery might be unreliable. So that can be explained with a simple example, as your professor has also explained earlier, that whenever a node is in a network is trying to transfer the data from one node to another, so it is not a very simple network. The networks are usually in a real world very complicated, and so they have multiple nodes connected to each other. So these nodes are able to communicate or transfer data from one to another. However, they have multiple requests. So it might be the case that that here is one node, then here is the other node, and there is network traffic coming from one direction, then another direction, then then another direction. So all the direction there is a network traffic, and it has to move give the data from this one node to the another node. However, there might be a case there is the bandwidth allowed of only 2 Mbps. So it is not allowed to send all the data at one go. So there might be a situation arising in which the data gets stalled. These are the data packets which get stalled, and only this packet is transferable. And so there is a timeout. I mean, who's the node which has sent the data from this point to this node? It keeps on waiting for the acknowledgement that the data has been transferred, but due to the network traffic, it is not able to transfer that data, so the packets drop. So this connection is removed, and the data is not delivered. So the network is able to transfer data. However, that data delivery might be very unreliable. So for the reliability of data, transport layers comes into picture. It helps to transfer the data from one node to another, but with a reliable data delivery. So it keeps on checking what is the data which has not been delivered, and it retransmits that data. So for that, it obeys flow control and the congestion control protocols. So we'll discuss about them in detail next. And then transport layer also offers the service of ordered packet delivery. So it's the case that in what manner the packets are arriving. That is one, then two, then this is three, then four, then five. So in the same order, the packets will be reaching also. One, two. It is not the case then that three will be missing, and then four and five comes, or the order will be five, then four, then two, then one, then three. So this out of order delivery is not followed in transport layer. So it helps to maintain the ordered packet delivery. So now these are the major services which are provided by the transport layer protocol or the TCP. Okay. So however, in case of UDP, that is another protocol for the transport layer services that only obeys end-to-end packet delivery. So there might be the cases in which the application asks for the data delivery at a very faster speed, but it does not need that the data should be delivered at a reliable rate. That means that all the data packets are delivered. Only a few packets if delivered, that will serve the purpose of the application. So that thing is conveyed or done or managed by the UDP, that is user datagram packet protocol. So first we will start with the connection establishment. The transport layer obeys the service of connection establishment. So the connection in what happens in connection establishment is that it helps one device to connect to another device. So the connection means that the device can listen to the other device or the device can send a request to the other device, so that you have made a connection and now you can communicate with each other. So that building up of connection is done by the transport layer itself. So any questions till now? Okay, any questions? Akshit, you mentioned you have without. Yeah, what's the query, Akshit? You can unmute your mic now.
Hello, ma'am. Hello.
Yes, I can hear you.
Ma'am, UDP is used at transport layer
Right.
and same thing, unreliable delivery is used at data link layer also. So what's the difference between UDP and this data link layer protocol? No, data link, nahi, network layer protocol.
Yeah, so the network layer protocol follows the same thing, but I just mentioned a case of the network layer protocol where that is a possible that something is delivered, but there might be a case in the network protocol that it helps to make a network between a route between the two nodes, but it might be the case that the data there is no delivery of the data. Okay, because there is a congestion, and at that congestion it is not able to communicate any data. So that thing is managed by the UDP, that sits at the top of network layer in the transport layer, that the two end devices can communicate in a way so that it can transfer data as well.
Okay, ma'am. Thank you.
So what happens in a connection establishment phase? Like last time we have studied about the client server architecture, and so in that client server architecture, server always listens to what is the request being made by the client. So the client sends a connection request to the server, and the server then listens to that connection request and then gives a acknowledgement back to the client that the connection is established. So this finally established the connection. So this is very simple or primitive connection establishment. That is the one-way handshaking protocol. That is one-way means it sends the connection request and it receives back the connection acknowledgement. So this is very simple and there is no issue in the one-way handshaking protocol. But in real time, this doesn't work. There are multiple connection requests and there are multiple losses of the packet as well. So there is a situation in which you consider the scenario when the network can lose, or that means the packet can get lost when it is sent from the client to the server or server to the client. Then there is a case of delay, that the packet which is sent, that is got interrupted by the network and it obeys the delay, and there is a certain timer which is set at the server end as well, which says that at this time, timeout timer, if the packet is delivered then it will take, otherwise not. So if there is a delay, then again the connection will not be established or the packet is corrupted in between. And and the last case, which is about the duplicate packets. That means for the first case, if say the packet get lost or get delayed or corrupted, and then the timer gets timed out, and then again the client sends a next request to the server. So there might be the case that the first packet is delayed for some duration, but it again is uh, sent back to the server. So now the server gets to see two packets from the same client. So now the underlying network layer uses the reliability data delivery here. So we will see how we develop the connection establishment here. So here what we do is that we retransmit the connection for ensuring the reliability. So every packet use different paths to reach the destination. So then we see that the packet may be delayed and got stuck in that network congestion. And after the timeout, the sender, as I said, the sender assumes that the packets have been dropped and transmits that packet. So it may happen that the server has crashed and reinitiated the connection. So distinguish between the two is the main essential task, like which connection request is then prime. So it cannot make double connection or duplicate connection. So how that differentiation is done, we see it next. So to deal with these duplicate packets and how to recorrect them, we will see next. But for correcting this and establishing a proper correctness, these time delays are followed. And to improve, we have to make a balance between the protocol correctness, so that the correct establishment is done, and versus the protocol performance, that it is done in the least time taken. So the delayed duplicate creates a huge confusion in the packet switching network. So the major challenge in the packet switching network is to develop correct or at least acceptable protocols which can handle these duplicate packets and with less time, so that the protocol performance is also high. The first solution is to use the throwaway transport address, that is the multiple port number. So it might be possible that we send a one connection request with first port number, and then we again send another connection request with another port number, say 7180 and 7190. So the user end will be able to differentiate what is the latest request and what is the previous request, and it will try to accept one of them. However, this solution is very infeasible in real world because there are limited number of ports, and if we give multiple port numbers, so that will be exhausted. Then the next solution is that to give each connection a unique identifier, which is chosen by the initiating party and put in each segment. So whenever we are transferring the giving a request, a unique identifier is chosen and sent along with that segment. So the problem in this unique identifier is that at what identifier will be choosing and how to differentiate between then that identifier, then we will see later. Then the third solution is to devise a mechanism to kill off aged packets that are still hobbling around, that is restrict the packet lifetime. So whatever packet we are sending, we send a packet with a particular lifetime, and it will get timeout if the lifetime exceeds, the packet gets killed. So this makes it possible to design a feasible situation. So there are three ways to restrict the packet lifetime. First one is to prevent packets from looping. So that bound the maximum delay, including the congestion. Then putting a hop count in each packet. So we initialize the maximum value to each packet and decrement each time the packet traverses a single hop. That is a single node. Like for example, if we give the hop count to 7, then for the next node it gets hop count 6, then next 5, then next 3, and whenever it reaches a hop count of 0, the packets get dropped if it has not reached the source destination. But before getting a hop count of 0, if it reaches the source destination, then the packet is received. And the third way is to timestamp each packet, that is define the lifetime of a packet in the network that needs time synchronization across each router. So connection establishment is that handling how to handle delay duplicates. We label segments with the sequence number, that is the unique identifier that will not be reused within t seconds. So we give the unique identifier and we also set the timer along with that particular request. So the period t and the rate of packets per second that needs to be sent determine the size of the sequence number. So at most, one packet with a given sequence number may be outstanding at one given time. So two most important requirements that needs to be considered, that sequence numbers must be chosen such that a particular sequence number refers to more than one byte for one byte sequence number at any one time. So one byte means either 0 or 1. The sequence number must be refers to as more than 1 or 1 byte. So the sequence number is decided based on, as we say, the period and the rate of packets which needs to be sent. So if 7 packets needs to be sent, 0 to 7, then the 3-bit sequence number will be given. So we'll see how. So how to choose the initial sequence number in case of delayed duplicates. Now we'll see few examples. Then that how to create the initialize the next sequence number. Okay, any confusion till here? These are the basics that you have already covered in your previous lectures. I'm just re-revising the concepts, giving you a basic idea so that we can solve the corresponding assignment. So initial sequence number during connection establishment. So a delayed duplicate packet of connection 1 can create a confusion for connection 2. So it might be a case that when we are sending a packet for connection 1, it gets crashed in between and we have given a sequence number to that packet. So that sequence number can then be used by the another, what is the next sequence number that can be initialized for building up another connection. So there is a lifetime which we have seen for a particular sequence number. So it crashed at this point, as you can see here. Uh, it crashes at this point. So when if we there is a possibility that this is the connection timeout, and there is a possibility that the connection can be revived back. So if we give the initial sequence number at this point, so that will be duplicate with the this sequence number if it is revived back. So then we cannot choose a sequence number till the connection one timeout is ended. So we have to select the sequence number after the connection one timeout is ended. That is this point. That is parallel to the packet transmission rate of this first connection. Because if it is not parallel, it is overlapping. So this will be the area where there is a possibility of overlap sequence number. The another solution is we give a sequence number more than the sequence number which are here, that is above these values, so that there is no overlap in this corresponding zone, and we give a sequence number above this particular sequence number zone, so that there is no confusion in between them. So here we see that the receiver receives two segments having the same sequence number within a duration d. Okay, so one packet must be duplicate, so the receiver discards that duplicate packets. Now we see, for a crashed device, the transport entity remains idle for a duration t after recovery to ensure that all packets from the previous connection are dead, and then restarts after this point. So, however, if it restarts after this point, that is in parallel to this, in the same line of transmission, but there might be a case, adjust the initial sequence number properly. So the host does not restart with the sequence number in the forbidden region. Based on the sequence number, it is used before the crash and the time duration t. So then if it starts after this, so there will be two possible problems: that the host sends too much data too fast on a newly opened connection. So there might be a case, I'll just see here, that the rate of transmission of the source is this, and the rate of transmission of the other source is this. So if it is parallel to this, however, it is transmitting very fast. So there might be a case that the actual sequence number, the previous connection goes very fast. So initial transmission rate was this, however, then the transmission rate exceeds in this direction, that is fast. So there might be a possible there was a crash at this point, at some point like this. However, later the crash is recovered, and then it follows a speedy transfer of data, and then we have started a new connection here with this sequence number, and this is again the overlap region that we can get. Or there is another possible source that the later part give it like too slowly. So in that case, like it starts at this, but its rate of transmission is this, that means too slowly. So the this is again an overlap region. So the solution that we choose a sequence number within this timestamp, after this timestamp, is a wrong solution, which might gives us packet sequence numbers which are out of order and in the forbidden region. So for this, we have introduced the three-way handshake lemma. So what is the three-way handshake? So in this, just a second. Okay, by looking at the acknowledgement, host 1 ensures that the sequence number X does not belong to the forbidden region of any previously connection establishment. So this is the scenario in which it gives the connection request to from host 1 to host 2, and then it reads with the sequence number X, and then it receives the acknowledgement with the sequence number y and the acknowledgement of sequence number x. So here the receiver, this host one, identifies that the sequence number x does not belong to the forbidden region of any previous established connection. So by looking at the acknowledgement in the data, host 2 ensures that the sequence number y does not belong to the forbidden region in the of any previous established connection. As you can say, then the connection is established and it transfers the data with the sequence number of x and acknowledgement of y. That is the acknowledgement of y that was received earlier with the sequence y received earlier. So this is the three-way handshake protocol that we obey further. So there is a case when connection request is a delay duplicate. So in that case, they send a request with one, and then the host one gets an acknowledgement with that particular X. But there is a this was the old duplicate that was received. So then it knows that it is the old duplicate and it rejects the particular request and does not transfer any data. It rejects that particular request. There might be a case of the old duplicate when we are giving back the data. So there might be a case where the data from the old duplicate has old transmission has been crashed and now it is sent again. So now, but you can see here it is from sequence X only. However, it is giving the acknowledgement of Z. However, here the sequence was sent with the sequence Y. So then again it rejects and with an acknowledgement of y. The final phase is the connection release, that is the asymmetric release. So one party hangs up and the connection is broken. So one way is the asymmetric and another way is the symmetric. In the asymmetric field, there is this connection establishment, then the acknowledgement, and then the data transfer. And then there is a certain time where the data is not transferred, that no data are delivered after a then there is a directly disconnection request from the host 2 and the connection gets disconnected, broken, and no data is transferred from host 1 to host 2. This is the asymmetric release that either host 1 or host 2 can directly put up a disconnection request at any instance of time. So next is the symmetric release. So the drawback is that in the asymmetric release, there might be a case when you have the when the host one has already sent the data. So and it does not it wants that data to be sent. However, the host two sends a disconnection request, but the data has been lost by the host one. So for the symmetric release of the connection, we treat the connection as two separate unidirectional connection, which requires each one to be released separately. So does the job when each processor has fixed the amount of data to send and clearly knows when it has sent the data and when it has done. So what this protocol is done, so the host one says that I am done with the data, and then the host one also acknowledges that I am also done with the data, and then the connection is released. So here the host one sends the DR request, that is connection and disconnection request, and then the sender host 2 again acknowledges it and sends the disconnect request. And then if it is both the requests are reached, they are also started with a certain timer. Within a certain timer, if they are acknowledged and reached to the host 1 and host 2, then the host 1 gives an acknowledgement to the host 2 that to release the connection, and then the connection gets released at both the ends. So there might be a case where the host 2 has given the disconnection request to host 1. So it releases the connection and sends the acknowledgement. However, that acknowledgement gets lost So the host 2 will wait till the timeout, and then it will finally release the connection itself. There might be another case in which the request from host 2 to host 1 has lost. So then again, the host 1 resends the disconnection request to the host 2, and the host 2 again acknowledges with the disconnection request, and then there is a release of connection at both the ends. And all the that means that there it needs to be retransmitted. So there might be a case when the response is lost from the host 2 to host 1, and then again it retransmits from host 1 to host 2, and then again it gets lost. So all the requests are getting lost, and host 2 waits for a certain time, and after timeout it releases the connection, and host 1 also after n timeouts it releases the connection. So connection releasing is a bit of simple process. It just waits for the timeout and then releases the connection. So anyone having doubt till here? Next we will uh, switch to this flow control. You're asking what does the forbidden region represents? So for forbidden region is the basically the region in which you cannot choose a sequence number. So as I've shown here in the example also that this is completely a forbidden region. Okay, so here if you have given the example also, if you start a sequence number from here again, you assume that the data transfer is at this rate, it is parallel to this and it will not collide. But there might be a case that the data transfer rate of the initial request is speeden up or it gets slowed down. So with the both the possibility, this is kind of a forbidden region. So the best possible case to choose the sequence number is next to the crashed sequence number, not parallel to it after a certain timeout. So this is the region of forbidden region. Okay, I assume everyone is clear till here. So now we will see the next service which is being provided by the transport layer, that is the flow control at the transport layer. So till now we have discussed that the what is the flow control basically. So there, yeah, I'll show you here. So assume that this is node 1, okay, and this is node 2, okay. So node 1 is giving sending the data at the rate of 2 Mbps, okay, node 1, and node 2 is receiving at the rate of 8, and then it is transmitting at the rate of 10, then at the rate of 5 to another nodes, okay. So that there might be a case that uh, or this might be a case that this gives at 10 Mbps and this received at 1 Mbps, okay. So when you are sending with a higher bandwidth, the node 2 will not be able to receive at that higher bandwidth. So to control that flow, that is known as the flow control, that you reduce the bandwidth and then transmit at a rate at which the receiver node is required at. Okay, so because if there is a higher flow, there will be a lot of congestion at the receiver's end, and some packets will get lost due to the timeout service. So that will lead in an unreliable connection at the network layer. So the network layer in this manner possibly provide an unreliable connection. So to make it a reliable connection, at transport layer we follow the TCP protocol, and this reliable connection is maintained at the transport layer. So they maintain firstly the flow control and then obeys the reliability. So for this, they follow the stop and wait flow control protocol. We see the how the stop and wait works for the error free channel in which there are no errors. So here the sender sends a request with a frame to the receiver. The receiver receives the frame and acknowledge it with an acknowledgement to the sender. The sender receives the acknowledgement, then it again sends the next frame, and the receiver receives the frame and then again sends the acknowledgement which is received by the sender. This is how stop and wait flow control works. At there, we send one frame, gets acknowledgement of that frame, and then sends the another frame, and that gets acknowledgement of that frame. That means we send one, then gets acknowledgement, and then sends two, then gets acknowledgement, then send three, then gets acknowledgement. But this is a very ideal scenario where there is no error in the channel. So when there is a noisy channel and you send frame 0, gets its acknowledgement, then send frame 1, gets its acknowledgement. Then you again send frame 0, but it gets lost. So for that purpose, we use sequence number. So in this stop and wait protocol, because we can send one frame at a time, we use the sequence number to individually identify each frame and its acknowledgement. So the maximum size of the sequence number can be 2-bit, that is 0 or 1. So this is this method or this channel is called automatic repeat request. That means, as we have earlier discussed also in connection release, if for a certain timeout it sees that there is no acknowledgement for that particular frame, it again retransmits that frame, and then again the acknowledgement comes, then again transfer another frame and the acknowledgement comes. So there might be a case when the acknowledgement is lost, then it waits for a certain timeout and then again retransmit that frame from the sender. So this is how the stop and wait flow control protocol works in a noisy channel. So here is the case where frame 1 was transmitted earlier also and frame 1 is transmitted again also. So B discards the duplicate frame and consider only one of them. So it is very tiring sometimes that in a stop and wait protocol operation, only one packet it sends and then receives again, sends another packet. So that is a very time taking process and a very tiring process. So now we see the stop and wait protocol with a pipeline version, that is the sliding window version. That means the pipeline data packets are sent all together and we get the pipeline acknowledgement for those data packets. So we study the sliding window protocols. What till now I assume everybody is clear. My screen not working. So the last thing we'll be discussing is the sliding window protocols. So in sliding window protocol, each outbound segment contains a sequence number, that is from as we said, we send the chunk of the packet, that is not only a single frame. we send a chunk of frames. So for this purpose, like we send a chunk of frames, like sequence number for say it starts from 0 for the sliding window, then 1, then 2, and so on. Okay, so it follows to a maximum sequence number of 2 to the power n minus 1. So for example, if there are sequence number with 3 bit, okay, so how many possible sequence numbers can be there? That is 2 to the power n, that means 3. 2 to the power 3, that is 8. Total 8 sequence numbers are possible. So if it starts with 0, it will go up till 7, that is 2 to the power n minus 1. So for every sliding window protocol, the sequence number follows the same outbound segment from 0 to a maximum of 2 to the power n minus 1, where n bit sequence number is there. And sender maintains the set of sequence number corresponding to the frames it is permitted to send, that is the sending window. And then the receiver maintains a set of frames it is permitted to accept. So here the sender has a certain window, that is a sending window, that it sends. Like for example, this sender window is of 2 and 0 1 it sends, and then again that window is implemented at the receiver's end, 0 1, that is the receiver's window. So this is how the sliding window protocol works, sending window and the receiving window. We have the window size of 7. So it is sending 0 1 2 3 5 6 till 6. So frame 0 is sent, and there is a window maintained at the receiving side, which is the receiving window. It receives this 0 frame, then again it receives frame 1, sends an acknowledge. Whenever you receive the acknowledgement of that frame, then only the window is pushed forward in one step. So then we send frame 2, it receives acknowledgement of 1, and then it shifts one step. Then send frame 3, frame 4. So it has received till 0 1 2 3 4. So when it sends the acknowledgement of 0, at that moment it shifts one window, one unit. When it sends the acknowledgement of 1, it shifts one unit. So this is how the sending window and the receiving windows shifts and obeys the sliding window protocol. So how does sliding window protocol works in the noisy channel? So everyone clear about this sliding windows, and I mean sending windows and the receiving windows, because this is a difficult concept and it is an important concept in this computer network. So if anyone has any confusion, just ask. You can ask now. What do you mean by ARQ? ARQ I've already mentioned earlier. That is mentioned here, automatic repeat request. That is that means if a packet get lost at certain time, so the this sender side waits for a certain timeout and then again retransmits that packet. So that means automatic repeat request. So the stop and wait protocol follows automatic repeat request. That is meant by ARQ. Okay. So in noisy channels, a timeout occurs if a segment gets lost. As I said, if the acknowledgement or the segment that gets lost, it sees for the timeout and then retransmits the packet. So how does the flow and error control protocol handle a timeout? So there are two ways to handle the timeout and how to retransmit those packets. One way is a go back N ARQ, that is automatic request repeat request. In this case, if a segment n is lost, for example, all the segment from 0 to n, segment n are retransmitted again. That is start of the sliding window. For example, if we are transmitting a sender window of 1 to 4 and a fourth packet get lost, so again all the packets from 1 to 4 will be retransmitted on that channel. That is go back N protocol. And second one is the selective repeat ARQ. That is only the lost packets are selectively retransmitted. That means not all packets are retransmitted, only the packets which were lost are retransmitted. So for that purpose, the negative acknowledgement or the selective acknowledgement is sent from the receiver side to the sender side, so that it gets to know or inform the sender about which packets needs to be retransmitted. So in go back in ARQ, it sends a frame 1, then frame 2, then it gets acknowledgement from frame 1 and frame 0 and frame 1, and then again it sends frame 2 and frame 3. However, it does not receive the acknowledgement from frame 2, and the sliding window is for the so it sends all the frame again that were in the window. That means after 2, 3, and 4 were sent, so it will be resent again. That is frame 2, 3, and 4 will be resent again. So now we will see these terminologies. What are the outstanding frames? These are the frames that have been transmitted but not yet acknowledged. So in this case, the outstanding frames were 2, 3, and 4. They were being sent, but they were not being acknowledged. So the maximum sequence number that what will be the maximum sequence number? Okay. So total number of packets will be maximum sequence number plus 1. Distant sequence numbers are possible there. As I mentioned, because it starts from 0, so it leads to 2 to the power n minus 1. So total maximum sequence numbers is still maximum sequence number plus 1. So the maximum number of outstanding frame is equivalent to the window size. So if a window size is 3, so there will be always 3 outstanding frame. If a window size is 4, then the outstanding frames will be 4. Example, a sequence number 0 to 7 with a 3-bit sequence the number of outstanding frames will be 7, not 8. So as I mentioned, the outstanding frame are the frames which have been transmitted but not yet acknowledged. And in the go back ARQ, the this is maximum number of outstanding frame will be the window size. That is the maximum sequence numbers which we have. So by we choose the maximum window size equivalent to that maximum sequence number, but not more than that, not maximum sequence number plus 1. Like here we have seen that we choose the window size equals to maximum sequence number, not more than that. So if we choose the window size here, the maximum sequence number is 3. It is 2-bit. So from 0 to 3. So the maximum window size if we choose as 4. So here 0, 1, 2, 3 will be transmitted in a particular window. Then 0 will be sent. Then 1 will be sent, 2 will be sent, and 3 will be sent. So we did not receive, it sends the acknowledgement of 0, but it is not received. Then it sends the acknowledgement of 1, it is not received. Then it sends the acknowledgement of 2, but it is not received. It sends the acknowledgement of 3, and it is not received. So it will wait for a timeout, but it will again retransmit 0. However, all the packets are sent there. So that will lead to the duplication of packets. So that is why we choose a window size equals to max sequence number. So now there is a window size equivalent to the max sequence number. So if we get 0, then the 0 gets acknowledged, then 1 gets acknowledged, then 2 gets acknowledged, then 3 gets acknowledged, then 2 gets acknowledged, and then the sliding window shift for 3. So then it discards the wrong frame correctly. In a selective repeat protocol, it only sends the packet which have been sent out for the that has been dropped out. So if we send frame 1, frame 0, and frame 1, and sends the acknowledgement, and then the frame 2 gets lost. So then we send the frame 2 and frame 3. So now it will send the reverse, that is negative acknowledgement, that the frame 2 was lost. So only the frame 2 will be resent again, not frame 3 will be resent again. So the maximum sequence number here also will be maximum sequence plus 1, from 0 to maximum sequence, and the maximum number of outstanding frame will be window size, and which can be maximum up to maximum sequence plus 1 by 2. It again has a proof similar to the proof as I defined earlier. So say a sequence number is 0 to 7 with a 3-bit sequence number. So maximum number of outstanding frames or the window size will be equal to 4. That is maximum sequence number plus 1 divided by 2. That is 7 plus 1, 8 divided by 2. Now we will see two questions based on this afterwards. Firstly, we will discuss the assignment corresponding to the current session. So flow control is mainly implemented at which layer? Physical layer, application layer, transport layer, or the session layer? Okay, so sliding window protocol is associated only with the transport layer, not the data link layer. Flow control is mainly implemented at C, that is the transport layer. In a sliding window protocol, if a sender window size is made 10, then how many frames would be in the window after transmitting 10 frames? Everyone, please answer. Yes, the answer is A. No frame will be left if we have transferred all the frames together. which are true for go back and ARQ if window size is greater than n. Here I mentioned n is the uh, to the point where, okay, now you answer. All the segment from 0 to n are retransmitted if segment n is lost. Or all the segment from 1 to n minus 1 are retransmitted if segment n is lost. All the segment from 1 to n are transmitted if segment n is lost, and all the segment from 0 to n minus 1 are transmitted if the segment n is lost. The answer is A, that all the segments from 0 to n will be retransmitted after n is lost. So in go back and ARQ, all the segments from 0 to n are retransmitted if the segment n is lost. Okay, you understand these points. The next question is, what is the maximum data rate on any connection per clock tick? Inter-packet transmission duration. One segment, two segment, three segment, or four segment. Maximum data rate. We can transfer one segment, two segment, three or four segment. Answer is that we can transfer only one segment at a time. Otherwise, there or and the packet will get lost. The next question is, timestamping a network packet is necessary for A, enabling time synchronization across router and network layer, for defining packet lifetime. The answer is C, both 1 and 2, enabling time synchronization also and for defining packet lifetime as well. The time stamping is required for both. So the next question is that if a selective repeat has maximum sequence equals to 15, what is the window size? So for selective repeat, the window size was max sequence plus 1 by 2. So here the answer is 15 plus 1, 16 divided by 2, that is 8. I assume everyone has given the correct answer. Right. Transport layer is implemented in a firmware of a computer system. Correct answer is true or false. Correct answer is B, false, because transport layer is implemented in the kernel level, that is software level of the computer system. What is known as the outstanding frames? At frames that are yet to be transmitted, frames that have been transmitted but not acknowledged, or acknowledged frames, or none of the above. So the correct answer is frames that have been transmitted but not have been acknowledged are known as the outstanding frames. The delayed duplicate problem is there in TCP two-way handshake technique. True or false? Two-way handshake. So it is true. And two-way handshake, the delayed duplicate problem is there. So if a packet is lost and then it is retransmitted, it will not be able to identify what is being lost or what is not. So what is the window size of go back and ARQ with 4-bit sequence number? The answer is C. That is the 2 to the power 4 minus 1. That is the maximum sequence number. Okay, I hope everybody has given the correct answer. So good. Now we are done with these problems. So I have two questions for you. I would like if you take the time and just see the question. First one is, in a selective repeat protocol, every third packet gets lost while sending 10 packets. So like if we want to send 10 packets and in that thing, every third packet gets lost. So then how many total packets will be retransmitted in the selective repeat protocol? Anyone having doubt with the question? No, I said in a selective repeat protocol, every third packet gets lost. So they are sending a total of 10 packets and every third packet gets lost. So how many packet will be retransmitted in all? Yes, it is 3 packets. The correct answer is 3 packets. Not the third packet, it's 3 packets. So the next question is, in go back N protocol, every fifth packet gets lost while sending 10 packets. Okay, so the window size here is 3. I have given the window size. It is a defined question, so it is a variable window size. So we are sending a total of 10 packets, and the window size is 3. Then how many packets will be retransmitted? It's every fifth packet. It's fifth, not RD. It's wrongly written. Every fifth packet gets lost. So how many total packets that will be retransmitted again? And the protocol is go back N protocol. So take your time, like 5 minutes of time, and then uh, we can discuss this question. It's a bit interesting question. Take your time. Anyone with the answer? 6 packets, 16 packets, 6, then 15. So I'll give the solution. It's not, none of you give the correct answer. So, so the solution is as follows. Like there is sliding window of 3. So it will first send 1, 2, and 3 packets. Then first is sent. Then it will slide a window, send the fourth one. Then it will again slide a window, send a fifth one. So at this time, 5 packets are sent, and the fifth one gets dropped. Okay. So in go back N, the starting of the time window, sliding window till the N number is retransmitted. So here the start of the time window is at 3. So three first retransmitted packet will be 3, then 4, then 5. These 3 will be retransmitted again. So now 3, 4, 5 will be retransmitted. Okay. Then 4, 5, 6 will be retransmitted. Then 5, 6, 7 will be retransmitted. So here 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5. This is the fifth packet again. which gets lost. So here the sliding window is 5, 6, 7. So again we transmit 5, 6 and 7. 5, 6 and 7 will be retransmitted. Then next window 8, then next window 9. This is again the fifth packet which will be dropped, and then retransmission will be done of 7, 8 and 9. And then the 9th and 10th packet will be done. So this is how the retransmission is done, and in all the total 9 packets are lost. So anyone having doubt with this solution? If someone answered correctly also, 9 packets get dropped. Okay, so today we have completed the transport layer and seen the few of the services which are being offered by the transport layer. That is this flow control and connection establishment. So now, if any one of you has any doubt, we still have 10 minutes left. You can clarify. Yeah, the PPT will be shared in with you with the NPTEL team. Or okay, wait, I will share the PPT right now. I am not able to attach. So you can see the till the network layer, that is the IP address of the destination machine, and below the network layer you are not able to see the IP address. Yes, so I'll be uploading the PPT in the chat. I don't know why I'm not able to. Okay, so I will be doing it later. Last time we discussed about the port, that is the that means these are the information which are required by the transport layer, right? But it transport layers adds the header which gives a port to it. Yeah, right. Okay, I've shared the PPT as well. And the assignments as well. Okay, we can refer these. And the recording will be available at the NPTEL PMRF live session. You can get the recordings from there. Okay, so let us end the session now. If you don't have any doubt, you can leave the session. I will stop recording. Thank you for attending the session. Session regarding paper pattern that I cannot deliver because I have no clue what are the patterns of the paper, because there's those are set by the professors and the TAs which are affiliated with it. I'm just about here to clear your doubts and conduct a live sessions in which you can uh, ask, or I can discuss some questions and you can ask some doubts. That's it. Thank you, Deepa, and I thank you for all attending the session. And then I can stop the session and